Alright, so this is a question. We have nine consecutive integers, and we ask how can we partition it into two sets with, okay, they say show that no products of the elements, oh my god, show that the set of integers can be partitioned into two sets with the product of the elements of the first set equal to the product of the elements of the second set. Alright, so let's do this. So we are doing argument by contradiction. So we are going to assume there is a set of nine consecutive integers that can be partitioned into two sets. So if we're in the actual exam and we want to solve it, we will do this. We'll do it like this. Uh, let's just see numbers that can give us that we can partition and see whether it follows the rule or it follows our assumption. It follows the question or it follows our assumption. We have 0, 1, 2, 3, 4. These are nine consecutive integers. No, that gap is too much. So sometimes in the exam, you just write like some test cases, 3, 4, 5, and see whether there's a pattern. And hopefully, you see there's a pattern, and from there, you can be able to solve the question. So these are like four sets of integers, four sets of consecutive integers. All of they all contain digits, nine numbers. So the first set we can't even use this first set. I just realized that because we are multiplying by zero. So one part will be zero, the other part will be a number greater than zero. So we can't even use this one at all. But for the second one, hmm, hmm, I actually don't know why I wrote this because I'm not actually ready to multiply this thing. And the way I'm looking at it, I don't think we can start partitioning it into multiply because we don't necessarily have to split it into two like this and multiply. And they don't like we can do something like this. We can do 1 and 9 in one set. And the other set is 2, 3, 4, 5, blah 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 blah, all the way to 8. So I'm not ready to start find all the possible ways you can multiply it. But one method I think we can use is because they said products, I think we can work with factors and prime factors. Usually when you are dealing with products, and let me not say usually, a handful of times when you're dealing with product, you can always put prime factors, consider prime factors and ordinary factors into your solution. So if we are considering ordinary we are considering ordinary factors or prime factors, I believe it's better we consider prime factors. You will notice something in these three remaining that I put. There are three prime, three, four, four prime factors. Okay, that's the wrong color. Four prime factors. Oh my god, four prime factors. So each the prime factors usually changed that, like we had an extra one and we lost one prime factor. But it doesn't really matter. So because we have like an even number of prime factors, there's a chance we might be able to split the prime factor. We might be able to split it into two different sets. That one part is equals to the product, one part is equals to the product, other part. But if you notice, I don't think that may be possible because now that I'm thinking of it, there are two possible things that you can see. We have like if we split it into two distance, we can have something like this. On one side you can have 2 and 7. On the other side you can have 3 and 5. Like these are not equals to each other. They're not equals to each, like if you multiply, they're not equals to each other. And what I'm just trying to point out is that the prime factors on the left hand side should be the same prime factors on the right hand side. And if you don't have the same prime factors on the left and the right, there is no way our product can be the same in the two different partitions. When I mean left and right, I mean the left partition and the right partition. I don't mean any other thing. Just simple analogy. So let's see if we can, if we will always, if these prime factors can lead us to something good, or we have to find another way to prove or disprove the question. So set, for the first set, we cannot split this into two prime factors. The reason is because we have 2, then we have multiples of 2, so maybe we not really bother about 2. Then we have 3, we have two multiples of 3, that's 6 and 9. We have 5 and 7. We don't have a multiple of 5, we don't have a multiple of 7. I'm saying multiple of 5 and 7 because this can potentially balance the equation, like balance this thing. Like if there's a 2 here and there's a 2 on the other side, or a multiple of 2, they can be potentially balanced. Maybe something else, another 2 can exist somewhere that can balance it. But in the case of 5 and 7, if there's a 5 here and there's a 7, if there's a 5 on the left and there's a 7 on the left, there is no 5 on the left, there's no 7 on the left, so you cannot balance. Like there's no way the products can be 2. So now we know that for sure this second set cannot be partitioned into two equals, two partitioned into 2 where the products are equal to each other. If we try it for the second set, we still have the same set of prime factors, and this time around we have a multiple of 5, but 7, we don't have a multiple of 7. That means on the left hand side there will be 7, on the right hand side there is no 7 or multiple of 7. It means that it can't work. So this one too can't also be divided into 2. Now for the third one, we have 3, 5, 7, 11. So we have multiple of 3, multiple of 5. Once again, we don't have multiple of 7, we don't have multiple of 11. And because we don't have multiples of those two prime factors, it means that 7 can be on one side, 11 will be on the other side. That means there is no way that the product on left and product on right are going to be equal. When I mean left and right, I mean left partition, right partition. Saying partition is a very big word for me. So that's just basically it. So I think now we can move go from proving or disproving if the left or right will be equal to proving that there will be one extra prime factor. In the second case, this one, in the second case and the third case, in the second case there were 2 like extra lonely prime factors. In the third case there was just one lonely prime factor. So we can prove that, so our goal should be to prove that there will be at least one lonely prime factor, because if there is one lonely prime factor, it means that you cannot partition it into left and right and the products will be equal. Then I noticed another thing. Since we are working with 9 consecutive integers, there are 2 cases. There is a case where the numbers are less than 9, or not say less than 9. There's a case where the prime factors are less than 9. That's this, this, and this. Then there's a case where the prime factors are not less than 9. There's a prime factor that is not less than 9. That's this one here. This one, 11, is not less than 9. And if we keep on going, if let's say we don't start at 3, if we start at something like 6, we'll have 13 in the mix. And like, this is what I mean. If you do 6, 7, 8, 9, 10, 11, 12, 13, 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 14. So we have prime, prime, prime. Once again, this one is even worse because we have 3 prime factors, not even an even number of prime factors. And we have this one is not a lonely prime factor. 7 is no longer a lonely prime factor. So let me circle it in gray. It's no longer lonely. But 11 is lonely, 13 is lonely. And if you notice, because these numbers, right, these ones here are greater than 9. So if we want to make them not lonely again, it means we have to add another prime factor, another like a multiple of them. But you cannot add a multiple of 11 again. There is no way a multiple of 11 or a multiple of 13 can exist. The reason I'm saying this is because the next multiple of 11 is 11 steps away, but we are only dealing with 9 numbers, so there is no way a multiple of 11 can exist. The next multiple of 13 is 13 steps away. That's 26. So, but we are dealing with 9 numbers, and 9 is less than 11 steps away. 9 is less than 13 steps away, so it won't work. So indirectly, if we can put it in like writing form, then we've seen that there is no way that this once there's a prime factor greater than 9, you cannot partition it into 2 sets that the products are equal, because there will always be a prime factor that is lonely. Or not necessarily, sometimes you may not necessarily have just a prime factor. You can have like maybe something like let's say 121. All right, so let's have another set of numbers. 119, 120, 121, 122, 123, 124, 125, 126, 127. I think this is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 127. Now look at, I don't know if these numbers are prime factors. All right, I know the even numbers are not prime factors, but now let's look at 121. Let's bring it here. 121, if you split it, it has prime factors 11 and 11. And if the only way you can get another number that is a multiple of 11 is 11 steps away, so there is no way that with this particular one, let's say everything here is a multiple of a prime factor, none of them is a prime factor, let's assume. But because there is one, just one, at least one, that has prime factors greater than 9, because this one exists, this 1 to 1 exists, there is no way you can split it into equal distance, because there is no other one, there's no other 11 times 11 or 11 times something that helps to balance it. There's no 11 times 10, there's no 11 times 9, there's no 11 times 12, there's no 11 times 13 that can balance it, because that's 11 steps away. But we are dealing with only only 9 numbers. I will continue with the part. The other part I want to say is when the prime factors are less than 7 and 9, that's 2, 3, 5, 7. I will continue with it in the other part of the video.